Today we'll wrap up the homework problems in homework 11. This is due Friday? No. When is this due? Monday next week? Which is a good time. So we'll finish up all the problems today. Not too many left. You know, if I can get everything done earlier, I'll probably let you go earlier. But we'll see. Okay. A few things that you need to know. It's just the concepts, definitions. Getting to the definitions from the example. Okay. That's a three-phase circuit. Okay, three-phase circuit, and it draws a line, a ground line over here, a reference line. It's asking for the current over here. So it's providing a voltage from the A phase, which is VM, 0 degrees. That's A phase. And B phase is VM, negative 120 degrees. And the C phase is VM 120 degrees, like this. And all these impedances are given, okay? So how do you calculate the current here? If I'm let's calculate the first one first, okay? 0.8. And this one is J 3.4, 79. This is J 55. Let's calculate this together, okay? So the VM is 240 degrees from start to the end. Let's get the numbers, okay? Instead of just showing you how to do it, let's get the number, get to the end. So 240 degrees for VM is the peak value. 0 degrees as a reference phase for phase A. So labeled as ABC, and these are, oh sorry, I should label that here actually, not here, because the source impedance has both resistive part and also the inductive part as well. So here's A, here's B, here's C. There's a line, draw a line. So this part is source, that's source. So this source impedance is extracted from the source, is a model. And from here is the line. That's a line impedance, and here's the load impedance. 3 parts, okay? So I think part A and part B can be a little bit straightforward, but we still will go through the calculations. And part D and part C is very confusing. So we'll get to that point really quickly. So now I think the first question is, what is the current in this line? So remember last time we talked about the three-phase voltages. These are just the 3 voltages being delivered to the 3 impedance as a load. So the load is also has 3 phases. Okay, so each one has 1 phase and delivered to one part of the load. And eventually merges to this reference point. So you have the common reference point for the source and load, like this. It's asking to calculate this one. So last time we already did it. It's asking to find out the current in here. So we're going to use KCL because I have 3 different lines, even though they are complex, impedance, right? But we can still find out the current by using voltage divided by the impedance. So IA equals what? It's basically 240 volts, and with 0 degrees divided by the impedance. So this add to this, and add to this, is giving you 80 for the resistive part of it. For the overall impedance, the resistive part is 80, and the inductive part is 1.6 plus 3.4 is giving you 5, and this is basically 60J, right? 60J. Okay, so how to calculate current from this point? Because there's just a one complex number, okay, and we have to use this one for all the 3 different phases. So I think it's worth that we just directly find out the phasor part, phasor form of it, so we can use the phasor form for all 3 calculations to make things easier. Okay, use the phasor calculator. You could also calculate manually, okay? But let's do this really quick. Not this one, sorry. It's gonna be rectangle form to phasor form, right? So the rectangle form, the real part is 80 by looking at this one. So it's 80 plus 60J. So 80 plus 60J. No J. Convert. It's getting 100. It's gonna be 240 0 degrees over 100. 36.87 degrees. Okay, that's the first, that's the IA. And for phase B, the values are 0.3, J 2.4, 0.7, J 5.6, 79, J 52. It just has a lot of components trying to scare you, but actually it's really simple, right? Okay, just induction and resistors, that's it. So now let's see the second one. Second one, which is IB, so the B phase current, IB, is 240 volts, 0 degrees over what? If you add them together, you can find out it's the same impedance. 60J. So we already know what this is, right? So we can directly calculate it. Oh, sorry. This guy is negative 120 degrees. But the impedance is the same, 36.87 degrees. We'll calculate all of them at once later, okay? So IC, so the C impedance is 0.4 here, J 2.8, 1.6, J 72, 78, J 50. Find out the resistive part of it is still 80, and the inductive part is 2.8 plus 7.2. It's not 72, 7.2. So 2.8 plus 7.2 is 10. 10 plus 50 is 60. So still the same. 240, 120 degrees this time for phase C. 80 plus 60J. It's giving you 240, 120 degrees over 136.87 degrees. Okay, so this becomes real divided by real. Definitely the amplitude becomes 2.4, and the angle, the phase part, just do a subtraction. So 0 minus this one is giving you negative 36.87 degrees, and this one is 2.4. This divided by this, and this becomes negative 156.87 degrees, and this one becomes 2.4. Can't do this one, so it's 120. 120 minus 36.87. 83.13. 83.13. However, I think I mislabeled it because I labeled it as a B, C as a positive phase. But I think the problem is trying to do a negative phase. So we can change this one to, but it's not making a big difference. So it's basically just this, right? Okay, so this becomes plus, this becomes negative, minus here. That's right, just a sign change. Okay. So A is 0 degrees, is here. This is A. And B is plus 120 degrees, is B. And C is negative 120 degrees, so it's ABC. Right? It's counterclockwise. It's positive sequence or negative sequence, like we said last time. It's negative sequence, right? Counterclockwise is a negative sequence. ABC, counterclockwise. It's a negative sequence or phase sequence. Okay, so this is how to calculate the three currents. Because of the KCL, you just directly add all the three currents together. So IO equals IA plus IB plus IC. Okay, so phasors, if you do multiplication and division, it's pretty easy. But for addition, you just want to use a calculator, right? It's making things a lot easier. This one. So this will be a phasor math operation. 2.4 with negative 36.87 degrees and 2.4 negative 156.87 degrees. And the third one, we'll add the third one to it later, okay? Let's try it now. 2.4, and the phasor is 83.13 degrees. So V1,
24, so 2.4.
oh yeah. 2.4, right?
Yeah.
Oh yeah, that's right. Yeah. Okay. So V1 plus V2, if we do a sum, so it's this, it's giving us this. So we plug this into here, so you can do it. Oh, it changes it. Let me do this one more time. It's almost 2.4, so let's directly use 2.4. So negative 96.87. So this time we are doing V2 plus V3. Okay, and sum. See what the numbers are. Can you see that? It's really small. I'm sorry for that. Let's see if I can zoom in. Yeah, I can zoom in. Great. Zoom in. So that's the amplitude. That's the angle. Okay. But the amplitude is like e to the negative 16th. It's 0, right? It's basically 0. Okay, so this is this plus. Anyway, we don't need to add this intermediate value here, right, anymore. So since we know it's basically just 0 amps. So eventually the answer becomes 0, but I still encourage you guys to go through this calculation because using phasors or complex numbers to calculate currents and voltages is very fundamental knowledge to be tested in your final exam. So definitely you should know how to do that. So now let's see the part B. Part B. So it's gonna start asking you, because remember I talked about the different nodes. So this is the source terminal, is a line terminal, and that's a load. Okay, pay attention to this because it can be really confusing. Sometimes it's asking for the voltage at the line, at the terminal, at the source. Okay, it's asking really specific questions. You just have to know which node you are looking at. Okay, so for example, this question. This could be easier because it's directly asking you VAN. Okay, VAN here. So remember, I labeled these source terminals as lowercase a's. So these are uppercase A's, B's, and C's. And this is N here. So VAN will be voltage here to here. And since you know the current of this guy, which is IA, is this one. So you use IA times 79 plus J 55. So you can find out VAN. Okay, so this is 2.4 times. We can convert that one to phasor. Rectangular to phasor conversion. So this is, look at this guy, 79 here, and 55 for the imaginary part. And this is giving us 96.26 with 34.85 degrees. Okay, and this one you multiply the real part and adding the imaginary part. So this becomes 2.4 times 96.26, 231.024. The angle is it's like 34 minus 34.85 minus 36.87, negative 2.02 degrees. Okay, so that's how you calculate VAN. So what about VAB? Look at it. VAB. You know VAN, you can definitely find out VBN, right? VAB equals VAN minus VBN. Why? Because VAN is VA minus VN, and VBN is VB minus VN, right? So this becomes eventually VA minus VB, which is VAB, right? So you definitely need to find out VAN, VBN. So VAN has been calculated. VBN is IB times this impedance. IB is here. IB times 79 plus J52, okay? Follow the same method to convert this to phasor and times the current. So you can find out the VBN, okay? And then plug VBN into here. And VN is already calculated, plug into here, so you can find out VAB. Any question on this? No? Is the circuit balanced or unbalanced? It's really specific, very specific question. You know, if you just look at the source, remember how do we determine it's balanced or unbalanced? Balanced It's three-phase. Requires what? Same what? Magnitude, right? Same frequency. (120 degrees apart). Anything else? That's it, right? So same magnitude, same frequency, 120 degrees apart. So if you look at this one, it doesn't tell you the frequency, but we just have to assume it's the same frequency. I think this is what is given over here. Yeah, just assume it's the same frequency, okay? And what about magnitude? Magnitude. Same, VM. You're looking at the source. Is it 120 degrees apart? Yes. However, you just have to know. I didn't know that as well, but it's just asking you if this is a balanced three-phase system. You just have to look at the source terminal instead of the source itself, because the source has an internal impedance. This is the model, right? It doesn't really exist. These are not physical components in the circuits. These are built in the source. So this is actually physically the source terminal. So we're basically looking at the source here, the source terminal here. See if they're balanced. Okay. Now here, if you just look at here, same magnitude, and 120 degrees apart, perfect, balanced. And it won't be balanced if you just look at this terminal, okay, as a source terminal, because that's the real source terminals you are using to drive the line and the load at the same time, okay? So if you definitely can look at the impedance. The impedance are not the same, so it's causing different phase shift, okay? If you look at this, see, this is 0.2 times 0.2 plus J1.6, and if we divide it by this phase, let's calculate and see what we're getting here. So that will be a lot of calculations. These are better way to do it. So we need to find out the voltage here, okay? So what we have to do is use the voltage here minus what are the voltage drop and see what the voltage here. We just need to verify probably two of them, so you can see if they are 120 degrees apart from each other, okay? The phase probably is fine, because if you look at the division, right? So the imaginary part divided by this one, you are getting the arctangent angle. So this becomes 8. And same here. So it's probably causing the same phase shift. I don't know if that makes sense for you guys. So the impedance is causing the same phase shift, because if you calculate the angle here, right? Like this divided by this is 8. 2.4 divided by 0.3 is also 8. So if you use the current, because the current definitely, if you calculate it, right? It's the current. They are 120 degrees apart from each other, right? Like this and this is 120 degrees, and this is 120 degrees. So the currents are fine. But however, if you look at this terminal, you have to use the current times that impedance. When you times the impedance, the phase is getting added together. So if the phase is creating the same angle here, and eventually the voltage drop, or the voltage drop's phase difference will be the same. So actually the phase part is fine. But however, what about amplitude or magnitude? So these currents are 2.4, but if you want to calculate the magnitude, you have to look at the magnitude here. So what about 1.6 plus square plus 0.2 square and 0.3 square plus 2.4 square, and so we just need to find out if they are equal, and I really doubt it. I doubt it. They're not equal, right? Let's take a look. (1.6) times 1.6 plus 0.04. 2.6. Okay? 0.09 plus 2.4 times 2.4. See? So it's causing a different voltage drop to the magnitude. But phase change is going to be the same. So in that case, you are getting different voltage values or amplitudes as its terminals. So it's definitely is unbalanced. But how to calculate it? I'm going to write down the equation here for you to calculate it, just in case you are getting different numbers. Okay. So how to calculate VA? It's basically just the VM, 240 volts and 0 degrees minus IA times 0.2 plus J 1.6, right? VB is 240 volts with plus 120 degrees minus IB times 0.3 plus J 2.4. If you want to verify the numbers in your case, which could be different to mine, right? So you can definitely do the calculation and find out the magnitude and phase differences between V and VB and see if they're balanced. So we just have to talk about this because if I don't tell you, it's asking for the terminal here, right? If you are treating it as here, then your conclusion probably, hey, it's balanced, right? But however, it's actually letting you looking at these terminals instead of here. So if you look at here, it's unbalanced. Okay. Any question on this? No? Very close, okay? Just have how many problems left? Two more. Oh, three more. Then we're done. We're done for the semester. So on Monday, I will probably cover more examples if you want to come. I'll see if Dr. Morris can get that final exam practice, whatever, copy to me, so I can do some reviews. But however, I probably know what he's going to put on the final exam. So we'll run some examples on Monday, and also during the review week, we have 2 lectures for examples. Make sure that we can prepare you for the final exams, okay? So problem 11.9. So what is given is balanced, and it's 3-phase. What else? It's called YY connected, but if you look at this circuit, we didn't stress on that concept. But if you look at this kind of connection, it's actually a YY connection. It's a Y for the source, and so Y for the load. Although it doesn't look like a Y, but you know that it's like 1, 2, 3, like 3 different branches. It's forming a Y connection. You can draw it in the Y shape. So it's a Y for the source and Y for the impedance, for the load. Okay, so it's a YY connected 3-phase system. So if you see this YY connected, you should know what that means. It's YY connected. And what is given is, so this starts getting confusing, okay? I cannot skip every single word here because it's just making a difference. The line is a line voltage at the source is VAB. So if it shows you VAB is better because whenever it shows you it's a VAB, you know that it's a source terminal voltage between these 2 nodes, which is right behind the source impedance. Remember, all the YY connected 3-phase systems, they are labeled in the same way. Keep that in mind. Okay. The first problem, the homework assignment provided the schematic, but for all the following ones, they didn't provide the schematic. But you should know that whenever it's asking for VAB, it's going to be the VA and VB here in between these 2 phases after the source impedance. See, this is the source impedance, line impedance, and load impedance, right? So VAB is the lowercase a and b is over here. And uppercase a and b is after the line impedance. and N is a reference node of the load, like this. Okay. Keep in mind, it's all labeled in the same way. So line voltage at the source, VAB. So thank goodness it's providing VAB. Otherwise, you are looking at the voltage at the source. It's going to be here, right? It tells you it's VAB, so you know it's over here. Okay, important. VAB is 90 square root of 3 and 0 degrees volts. And another one is the phase sequence is positive. So we covered this on Wednesday. So what does that mean? Remember? A, B, and C, like this, clockwise. That's the positive phase sequence. Otherwise, it's negative phase sequence. Okay? A, B, and C. That's the negative phase sequence. Just a definition. Okay? Remember this. So positive phase sequence means it's a clockwise distributed. So A, B, C. So A, if A is 0 degrees, so what is the what is B's angle? Very quick quiz question. Negative 120, right? Okay. Cool. Line impedance. What is the line impedance? Always think about this circuit. Line impedance is over here. Not here, not here. This is the load impedance. This is the source impedance. This is the line impedance. Always think about this circuit, okay? Line impedance is 2 plus J3 ohms per phi, whatever. It's just a unit. Don't confuse you. Like just 2 plus J3, okay? And the load impedance is 28 plus J37. Okay, so it's asking for VAN first. So this point could be N as well, or N, doesn't matter, lowercase, uppercase. So VAN. Right, so this is why it starts getting confusing. So think about it. It's only provided line impedance and load impedance. Where's the source impedance? It just didn't tell you, right? It's ignored. Yeah, doesn't exist. So it's ignored. It's just assuming that whatever the voltage is already provided here. So the voltage, that's whatever voltage here. Okay, is right as the voltage over here. So it's treating that internal impedance right in the source. It's not separating that from the source, which is fine. I mean, doesn't matter. You just need to know. I didn't know that, but I was looking at the solution. I got to know, okay, so there's no source impedance. If it didn't tell you the source impedance, you cannot assume a source impedance, right? That's why we have to cover this, otherwise it's super confusing. So for this specific problem, 11.9, there's no source impedance. There are just two impedances on the line. Line impedance and load impedance. That's it. Which is totally okay. Okay. So it's asking for VAN. What is VAN here? You can simplify. So one of the techniques you should learn about is you can simplify each phase into one circuit. So for example, if we draw phase 1 circuit here, or phase A, what does the phase A circuit looks like? Line impedance, right? And load impedance. And this is N. Okay? And this is A. This is capital A. Okay? Look at this circuit. A, capital A, load N. That's how you model it. So this voltage source is 90 volts with oh no, sorry, VAB. What is provided is, so this is not provided yet. You have to calculate it. It didn't tell you, right? It tells you the difference. It tells the difference, VA and VB difference. Concept or definition. One of them, okay? Line voltage at the source. What does that mean? It means VAB. Just have to know it. Okay? Definition. Line voltage at the source for this problem is VAB. It tells you this is VAB. So VA and VB, the voltage difference between these two nodes, is this much. This could bring up a really important derivation here. Let me go through that with you. So if you know VA and VB as a difference, like VAB, could you find out VA and VB separately? How do we do that? Think about it. You can go through this process briefly. Because what is given is, we know that it's balanced, right? If it's balanced, and it's a positive phase sequence. So which means A and B, if we assume that VA is 0 degrees, VB is what?
The same VA.
Yeah. Okay? Let me take a look at this before I make any further mistakes. So this is correct. Okay? So what's next? This is testing your phasor fundamentals. It's given, right? This equals 90 square root 3 and 0 degrees. It's given. So can we calculate VA? I'll give you 2 minutes or so, see if you can do it. Don't want to directly tell you the answer really quickly. Think about it, or just a few seconds. Where should you get started? Just manually calculate it instead of using calculators. Definitely you can, yeah. VA equals like 1, 0 degrees minus 1, negative 120 degrees. And that equals 90 square root of 3. And use calculator to calculate it easily, right? No problem. Okay? But can we do it manually? So these are what is this? Just 1, right? Okay? Minus what? Is it still valid? Remember phasors? E, J, theta equals what? That's amplitude, right? A and this equals what? A cosine theta plus J sine theta. This should be something on your cheat sheet, okay? Or remember it, doesn't matter. So this equals VA 1 minus cosine negative 120 degrees minus J sine 120 degrees as well, and that equals 90 square root of 3, 0 degrees. Right? So VA becomes 90 square root of 3, 0 degrees over 1 minus cosine negative 120 degrees minus j sine 120 degrees. That equals 90 square root of 3. 1 minus, I already calculated previously, so it's 0.5 minus j 0.866. Convert it to phasor form, you're getting 155.88 0 degrees over 1.732 with 30 degrees, and this is giving you 90 and negative 30 degrees. So that's VA. So if you compare with VAB, what's the difference? Can you draw a conclusion here? That's a very important conclusion from this chapter. Okay. What kind of conclusion? Just look at the magnitude. For a balanced three-phase system, the magnitude, right? It's the line voltage between lines will be square root of 3 times the magnitude of the node voltage of each line. Just look at the magnitude. This is VAB. VAB is the voltage between line A and line B. So magnitude-wise, if you know VAB and you want to find out the voltage at this node individually, you just use that voltage difference between A and B divided by square root of 3. Okay? That's the conclusion here. So we use this conclusion for the next problem really quick. But let's come back to this problem. VAN is basically VA. Do you agree with that? Because this is the reference point, right? So VA here, the node voltage compared to ground. So VAN is basically VA. So now we are done with VA, right? Or VAN. So that's part A of the problem. That's part A, done. Part B, calculate the line current in A phase. Can we do that? Let's look at this. Calculate the line current in A phase. This is just the one phase. See, phase A or A phase. You know the voltage, so the line current IA equals VA over the impedance, which is 30 plus J40, which is the two impedance added together. These two impedance added together. So it's basically the voltage, overall voltage divided by the overall impedance. That's IA. That's a line current. Okay. And part C, this is part B. Okay, part B. Part C has another confusing question. Make sure you pay attention to this. Line, so the definition, okay? Line voltage at the load. At the load. In A phase, in the A phase. I have to write every single word down here because otherwise it's totally different definition. So line voltage at the load in A phase. See part A, what did we do here? Line voltage at the source. Line voltage at the source. And eventually we are calculating VAB. That's the line voltage at the source. See? Line voltage is the voltage between lines. Okay, it's an easier way to remember it. Okay, line voltage is the voltage between lines. It's not a voltage on the line. It's a voltage between lines. So line voltage at the source. Line voltage at the source, which is the source terminal. Line voltage. VAB. Okay. So now let's look at the part C. I already hate it, but you know, it's good to cover it, otherwise you're getting confused, extremely confused when you're doing the homework. So line voltage, which is the voltage between the lines, at the load is what? Line voltage between the lines at the load. Capital A, capital B. So it's VAB, but capital A, capital B. I know this is confusing, but make sure you are calculating VAB, capitalized A and B. Can you do that? This problem didn't give you a schematic. This is everything given for the problem. How to calculate V, capitalize A and capitalize B. This is just the A phase, right? So for B phase, there's another circuit. It's asking for the voltage between these two. How to do that? So VAB equals what? VAN minus VBN, right? Okay? So it's basically VA minus VB. Okay? VA minus VB. You know the current, you know the impedance. It's not difficult to find out VA here. Easy. Same for VB. How do I find VB though? It's not given. It's a positive sequence, right? Yeah, so VB has a 120 degree phase shift, or negative 120 degrees. So that's the only difference. Okay? So find out VB from there, and then you do a subtraction. Okay, so this problem is not that bad at all. There are two left, but one of them is could be a little bit confusing. Let me show you how to do that really quick. Still have 3 minutes, 11.12. Well, 2 problems left. Just in case someone want to start working on it over the weekends. So let's cover one thing for 11.24 really quick. Okay, so it's introduced the concept that we talked about really quickly a few weeks ago. It's called complex power. Complex power. Okay. Complex power is different from just the power, V times I. It's not. It's not just complex V times complex I. So the complex power has a specific definition. It's V times I conjugate. Okay, so that eventually equals V. It's the angle difference, because whenever you do a conjugate for the multiplication, it's actually doing a subtraction to the phase, to the angle. Let me draw it. Let me just write it down for you. See how I can. What's the best way to draw it? Let's do this. V times I, because these are all AC, so it's okay to do this, right? VM and phase. V, okay, times IM phase theta I, conjugate. So when you are doing a conjugate, it's actually adding a minus sign in front of the phase. So it's basically giving you VM theta V times IM minus theta I. Why? Because A plus BJ conjugate is A minus BJ, right? So they have their angles is opposite. No, it's inverse from each other. So this angle is arc tangent B over A, and this is minus arc tangent B over A. You know what I mean? So by doing a conjugate, you are able to add a minus sign in front of it. So eventually, this becomes VM times IM, and you are creating something you are very familiar with. See, that's why this is beautiful. It's getting a phase difference from the voltage and current. Okay, and this, if you expand this one, it's giving you this. Cosine theta V minus theta I plus VM IM sine J sine theta V minus theta I. I can find out the complex power over here is basically a combination of the average power and reactive power. Okay, just need to know this. We'll talk about the more details about the last two problems hopefully on Monday. So be ready for that. But you are good for the first 5 pages right now. Okay. All right, see you on Monday.